All right. Hello, everybody. Sorry, I'm slightly scrambled. Thank you for checking. I tried just one small change just like 5 minutes ago, right before coming to class. And I didn't give myself enough time to really give it an effort. So if you say it's not working, I need to make some other adjustment. I think I know what it is from last time I was using it. I just have to play with it and test it with more than 5 minutes. Thank you. So um, we will do that. I will try again on Tuesday, and then a week from today, I should at least have it working by then, and that's when I will begin actually collecting and counting the attendance. Yeah. Somebody already mentioned you couldn't. It wasn't working for you, right? Did, okay. So the deal is in Moodle, I have to set some group, and I have to tell it to only allow some group. I thought it would just let anybody, and so I must have clicked the wrong one when I was in a hurry to set it up. Don't worry about it. Doesn't matter this time. What's helpful for me is that you gave it a shot to tell me that. So thank you. In the future, once we're rocking and rolling with it, should work every time. And if it's not working, then yeah, I need to know, and we'll deal with that. All right, so we are back from the intro now, and we're going to go dive right into really the meat of the class. We're going to talk about mass balances. Last time we even had our first kind of touching on what is a mass balance. So we're going to take a look again at that example problem just to see how it connects. But I wanted to give a slide where we really take a look at the big picture. When I say mass balance, exactly what do I mean? And why do people call these, quote, mass balance equations? They will often call them as a governing equation, right? So you might see that as well. I don't use that term so often, but really what we're describing is what equation can we use that describes the entire system or a piece of the entire system that we are looking at, and what components govern what happens to the mass. Where does it go? How fast does it go? Is it created? Is it destroyed? That's our governing equation. That's our mass balance equation. And this is always going to be a question about accumulation. We could think of the accumulation of water in a swimming pool, in a pond, in a bottle. In our class, we are going to take it one step further and talk about what inside that water might be accumulating. But the simple way, the first thing we can think about is just water, okay? If you put a hose into an empty swimming pool and turn it on, what's going to happen? If it's sealed, it will accumulate water for some time. If the hose is on, you have a continuous flow from that hose, it will continuously increase the water. Eventually, if there's no drain, or maybe you reach the drain point, then water will be draining out of the swimming pool. And if you give it some time, it will be going in at the same rate as it's going out. We have now reached a steady state. That's what we call it. The water in the swimming pool might be moving, might be changing, but it's no longer accumulating. The same thing for a bathtub, right? If you have a drain filled with water and you pull the plug, it's now draining water, and it is not at steady state. You have a negative accumulation of the water, right? It's going away. So when we talk about a mass balance, we're talking about the accumulation. The simplest example that I just gave you, or just water, we are going to go further than that because we're going to have something in the water that we're treating usually. But at the end of the day, we are looking at the accumulation of something inside what we would call a control volume. So we specify that it's the bathtub or that it's the swimming pool. You know, we don't say it's the house plus the swimming pool if we only care about what's happening with the swimming pool, for example. Or maybe it's just one swimming pool and there's several on this property. So we'll define that control volume so that then we can see what is crossing it. That's, if it's crossing it at a direction that's coming in, then it's an input. Doesn't really matter where on that boundary we're crossing. It could be crossing from this side. That's an input, right? If it's crossing the boundary going outward, then it's an output, okay? And so we're just going to track, and the very simple way to do that is to have an arrow coming in from the left, arrow going out from the right. Pretty conventional. In the example problem we saw Tuesday, we saw 2 inputs. That's certainly possible. You can have multiple inputs, you can have multiple outputs. A lot of times it'll be 1 and 1 because that's simple, but not always. Then what's happening inside this, what we'll call a reactor today, what's happening inside this control volume, if something is creating or destroying the substance or changing it, then we have a reaction occurring. Okay, in the problem last time, there was no reaction. We said it was not doing anything, but we could have a reaction up or down. Inside that volume. So we are almost always, in most of our problems, we will be dealing with a possibility of a flow rate coming in. This is volume per time. A concentration should be a mass per volume. Going in, some similar flow rate and concentration. Maybe we call this concentration on the left the C naught, the initial concentration. And then the C going out would be the final, or just the concentration there. A lot of times our reactor here will be mixed. So many times we will say this is well mixed, a little stirrer spinning it around. That simplifies a lot of things, as we'll see. So within this control volume, we have 3 things that can occur. We can have an input rate, an output rate, and a reaction. So when we describe our accumulation, we are going to say that the accumulation is going to be equal to, and by the way, I'm going to say the accumulation rate is going to be equal to the input rate minus the output rate plus whatever kind of reaction rate we have. And for each of these, I'll call it a rate. That means we're looking at the mass per time. If we come back to our simple example of filling a swimming pool, we have the hose, it's providing some flow rate. The concentration, we can just call it 1 because for every liter of water, there's a liter of water, okay? Then we say if it's at 1 cubic meter per hour at a fill rate, then that's the accumulation rate when there's no draining, okay? Eventually, when the swimming pool fills and is overtopping, it's overtopping at exactly the same rate as we're filling it. Then we have, okay, no, the accumulation rate is 0 because we've reached a steady state. To write out this equation, this is an essential tool that you'll use. We're going to talk about it this whole lecture and many more. But the essential tool would be to say in that control volume, in the volume here, what amount of change do we have? What is the change in concentration per change in time? That's our accumulation term. Could be negative, could be positive. Sometimes this will be 0, meaning we've reached that steady state. Stuff's going in or being created as exactly at the same speed as it's leaving or being destroyed. Okay, that's pretty simple, but I'm keeping it, I'm going to repeat it a lot because it's important, and within the context of a problem, you might lose the simplicity of that. So we can set that equal to what's going in minus what's going out plus whatever reaction we have. Another way to write this, if we are at steady state, we can say all the inputs and growth reactions are equal to all of the outputs and decay reactions. So we'll get there from this term. So we can say then V dc dt, we can see we might have some calculus here sometimes, will be equal to what's coming in. So if we just have the one input term, it'll be Q times C. If we look at that, that should give us a mass per time unit. On the left side of the equation, we have a mass per time unit. The volume times the concentration gives us mass, divided by the change in time. On the right, the flow rate times the concentration is mass per time. So we'll have what's coming in minus what's going out, QC, plus whatever reactions we have. And we're going to talk about the reaction term a lot today. Right now, I'm going to simply leave it as a generic rate of change of C. Okay? Today, a large part of the point of the lecture will be to describe how do we account for a rate of change of C, and what difference does it make if we use a different type of reactor, if the reactor itself is shaped differently. We have a different design for the reactor. So all of that's written out here. I don't know why I decided to write it twice, but it's right there. And if you see, if this goes to 0 for a steady state, then the inputs plus the growth will equal the outputs plus any decay. So if this is true, then we can write it that way. That's going to be pretty obvious when you stop and think about it. You didn't really need a class to teach you that. But we need to be taking these problems from this approach, because eventually we can then solve a more complicated problem to see, okay, well, how much has accumulated after 10 minutes if we have certain conditions? What flow rate do we need to achieve a steady state given the reaction is the speed and the volume is that big? This reaction term, by the way, that's going to be how much is reacting within the volume. So that will ultimately be a mass per time unit. And like I said, we'll talk more about that. Any confusion about this? Kind of making some sense? Okay. So just a glance back at what we did last time. Given that way of thinking about it, we had two inputs, an input here, and an output. We said there was no reaction. Bless you. So the mass balance became inputs equal outputs. The other thing we can say is we can stop and think about it. The word problem itself told us chloride is conserved, or is a conservative pollutant. Treating chloride as a conservative substance, assuming complete mixing. So the two streams mix completely. The chloride is not reacting, it's conserved. And presumably it's been going for a little bit of time. That means we should reach a steady state. There's nothing else that could change it from a steady state. So therefore, we did the inputs equal outputs. We could have started as a V dc dt equals inputs minus outputs plus the reactions, which were 0. So when we wrote all this, we didn't write all that out, but we could have. And then it would have gone to the same exact way we solved the problem, right? So I'm introducing it to you that way kind of for a second time to show you we can always use that generic mass balance approach. The accumulation is going to be set up that way. So let's talk about the reactions themselves, how to mathematically model a reaction. And the reaction can be, it could be chemical, could be physical, could be biological. There are all sorts of reactions that we could consider. So this is not necessarily one or the other, just some type of reaction that's changing the matter in a volume. Okay, that's what we care about. Then we have a few different types of reactors that we can place our reaction in, and it's useful to give them a specific term. You know, my water bottle here, we can do some reaction on a batch of water, on a jar of water. That's a bit different than if I had water running through a hose and some reaction happening inside that hose. The dynamics are a bit different. The math will be different about how we track what's happening inside of it. okay? And that's the type of thing we're going to explore with these mass balances. Okay, a few common terms. I've already talked probably through most of these, but common terms we should know. We use V for volume. That's going to be something like cubic meters, maybe liters, something like that. Gallons. I often stick to the metric units, but certainly there are times where we need our standard imperial units. Flow rate in Q, volume per time. Could be cubic meters per second, could be, sometimes you'll see million gallons per day, MGD. Concentration, C, is what we often use for some chemical or some mass per volume concentration. Sometimes we'll use N for the number of something. So the number of particles that are coming to stick together. It's almost, it's kind of different than a mass balance, and because we're doing a numbers balance, but we can treat them the same with some assumptions. Then the next up, we have what's called the hydraulic retention time. This one is usually, and our book uses theta for that. Sometimes people use tau. And this is defined as the volume divided by the flow rate. This, by the way, is one equation I'd like you to memorize. I'm not giving it to you on an equation sheet. It is quite simple and very important. Okay? This is theta equals V over Q. And if we look at the units, let's just use cubic meters and seconds for a moment as an example. We have cubic meters divided by a flow rate in cubic meters per second. This gives us a residence time in units of time, in seconds, right? So you should be able to derive this equation anytime you need it, because you should know hydraulic retention time is a time unit. And all you have to do then is remember that it's related to the volume and the flow rate. How long does the water exist in that spot given how much space it has and what the flow rate is? And again, you can think of this, if you're filling a little glass of water and you used a fire hose, you'll realize there's a very short residence time and now you're splashing it everywhere. Or, if you use a trickle of water trying to fill a swimming pool, well, that's going to take a while. The big volume, slow flow rate. Then if you get it full, that water is going to reside in there a long time. So you can solve it from there. This is very important. This will define a lot of our design for reactors, is this relationship. So memorize that. Or better yet, learn it, right? Maybe that's memorizing, maybe it's simply recognizing and memorizing the principle there. But that's a good one to know, hydraulic retention time. Okay, the rate at which something reacts, we can generically call that R of C. This is really going to be a change in C per time, dc dt, that we're going to put in the context of a volume, because dc dt is not by itself a mass per time unit. So we need dc dt times a volume to get to the mass per time that we need in our mass balance equation back here, right? Each of these components is mass per time, and so on. Accumulation rate is mass per time. To get the rate itself, the reaction rate, growth or decay, we need to take that plus or minus for the growth or the decay, times some reaction rate constant, times c to the nth power. This is describing dc dt, and then we put it in the volume. So when we write it out in our in a mass balance, we take R of C times the volume. And I think I should have placed that on the first slide. So I'll fix that in a moment. Because that gives us the rate of change of a concentration multiplied by the volume gives us a mass per time change. The rate constant K is just some principle. Maybe we have water evaporating, and the rate at which that happens depends on the temperature and the vapor pressure and stuff. So we'll have some property. It is usually constant given some situation. The rate at which chlorine disinfects some bacteria. That's a constant given the chlorine plus the bacteria. Okay, the rate of change of how fast bacteria multiply. We have a constant for that, and they double every so often, is how we might describe that. So the K will almost always be a constant. I mean, it will always be a constant. You'll either be given it, or maybe you solve for it, and it will be, it will provide units that satisfy the reaction rate being in mass per time units. So if we look here, I put an N. This N can change, and that's going to be the subject of a lot of what we talk about today. That's a different reaction order. If a reaction depends on how much stuff you have there, that, to what extent it depends on it dictates the reaction order. So if I give you $20 a day, that doesn't matter how much money you have, you're getting $20 a day. Your bank account gives you 1% interest. It matters how much you have there, because 1% of $10 is not very much. 1% of $10 million, well, now your actual mass per time change is very big, right? So this is reaction rate orders, and we're going to describe those more clearly and in more depth in a moment. Let me just flip back and correct. Here we should really have the volume term here as well. That gets us to mass per time for each component. One thing you'll notice is you can have more than one reaction. You can have a growth reaction and a decay reaction. Most of our unit processes, we simplify it down to just having one net reaction in one direction. Occasionally, when we get to the biology, we might have to think about, okay, well, the bacteria are dying, but they're also growing, okay, and we have to do some balance. But normally, we're just getting rid of something, or maybe just combining something, growing something. Okay, clear so far? Clear enough? All right. So back to the hydraulic retention time. Theta, like I said, this is the one you need to know. One of a few that I'm specifically telling you, please know it, and I'm not giving it to you on the formula sheet. So this is the volume divided by the flow rate. That gives us time. And we can take a look. Let me pull up this. Oops. We can take a look at what's called a tracer test. And essentially get an impression for what is happening with water flowing through some reactor. Okay, a tracer test like this, where we add some dye, some visible thing that we can see as it traces its way through the reactor, is we can see how long is it residing in there. And there are some fancy things you can do with the tracer tests. One of the things is to learn about the kind of the hydrodynamics. Are there spots where it's not very well mixed? Does some of the dye come out sooner? That's very important for non-ideal reactors. Most of what we're going to do will be with ideal reactors, assuming that it's all uniformly mixed and things like that. But what I kind of want to highlight here is the time it takes for it to come through. This is probably just some small laboratory demonstration thing, maybe this size. And you can see it's not flowing very fast. So you already have some intuition about that flow rate is pretty slow, right? This is maybe 1 liter after a minute or two, right? It's a slow trickle. So just giving you like the visual picture of what are we talking about when we're talking about retention time? How long did that dye stay here? Okay, and if you go more advanced into design of water treatment, these things become important, because you can see if this was chlorine trying to disinfect your water, whatever water is hanging out right around here is not getting so much chlorine. Okay, so it's something to keep in mind there. All right. So before we talk about the reactors, the shape and like that right there, we might call it a plug flow reactor. We'll come back to that. But I want to talk about the reactions themselves that we're going to put into the wider math. Some reactors might not have an input and an output. For example, if we treat my water bottle, so that's going to change the way we set up our mass balance here. So I want to go ahead and just start with the reaction term itself. Okay? When we talk about that reaction term, what do I mean when I say there's 3 different reaction orders? There's, in general. Generally, for our purposes, we're mostly going to deal with 0 or first order, very often first order. We will talk a little bit about second order. Sometimes those are important, they're a bit more rare. So what do I mean by the reaction order? That's this exponent. Whatever that exponent is the reaction order. Okay? So we can say a first order reaction depends on the thing that's reacting to the 1 power. Right? If it doesn't depend on it, if it's the $20 a week that I'm giving you, doesn't depend on how much money you have, that order is 0. It's a steady, nothing changes it, doesn't matter how much you have, you're just getting that. Okay? If only I had that kind of money where I could just give you all 20 bucks a day, right? Okay, so if we plot that, if we say for a 0th order reaction, could be a growth or decay, so we could say if we plot the concentration versus time, we'll start somewhere and we'll be gaining some steady amount over time. All right, and maybe, oops. If we have a negative, a decay reaction, likewise, we could just have some steady decay over time. Now, a first order, this is the example of money in a bank account, right, with interest. You're earning some percentage of what's there. So a good way to look at first order reactions, because we've dealt with it a lot, we kind of know what's going on there. We can just simply say the change in our concentration over time is equal to plus or minus k times c to the 1 power. So when we have a large C that it's acting on, then this becomes, our rate of change has increased, right? So let's consider we might start at 0 and we are changing with time. It might look something like this, exponential, right? This would be first order. Or decay would look something like this. When we have very little of it remaining, taking a percentage of it is not taking away a lot. Okay? When we go to second order, now we're on more of a power law kind of situation. And for the growth, generally becomes quite steep, quite fast. And again, this would essentially look like dc dt would be some rate constant times c squared. Right? Try to get a better drawing. or in the negative. All right, does that make sense? How many of you guys have seen this before? Kind of familiar? Does this still help a little bit, or just kind of already knew it? All right. Well, this will be important because sometimes we'll have problems that either tell us we've got some reaction order, or we have to discover it for ourselves. And there's a trick to discovering it based on what I said a few minutes ago about the rate constant. The K has to satisfy our units. So we have to be talking about mass per time units when we deal with these. So if on the left we have dc dt, on the right we need concentration per time. Okay, so if our reaction order is 0, K has to satisfy concentration per time. If we have C to the power of 1, then suddenly dc dt equals K times C. The K only needs to be 1 over time. So the K changes with the reaction order. Therefore, we know the reaction order if we know the units for K. So we'll see this in word problems where the units for K for 0 order are going to be concentration per time, something like milligrams per liter per second, as an example. We'll just say C is in milligrams per liter, and T is in time, in seconds. For a first order, again, the K has to satisfy everything except C to the 1 power. So that becomes K will be in 1 over time units, 1 over seconds, or sometimes you'll see this as seconds to the minus 1. If you see that, you've got a first order reaction. Okay? This is another thing you're going to have to learn to do with the word problems. For the second order, we can do the same thing. The K has to satisfy it such that on the left we have dc dt, concentration per time, and on the right we have concentration squared. Okay, so it has to go the inverse of concentration and give us per time. So K then will be liters per milligram in our example per second. It looks a lot like zero order, so don't confuse the two. Remember to just check your units. That's the best advice I can give you for doing well on the exams too. Check the units. Is it making sense? If not, can you use them to find some sense? All right, any questions? All right, so kind of talked through probably all of this already, but just to reiterate a little bit and show you also we can take the derivative and kind of find the next order. So 0 order reactions, this will be set up as dc dt equals K times 1, essentially. C to the 0 power is 1. That means the reaction rate constant is going to be milligrams per liter per second, or something like that. That means we have a straight line, and if we take the derivative of that, it will be flat, right? The rate of change does not change over time. So the rate of change is unchanging. For a first order reaction, same deal. K times the C to the 1 power now means that we have per time units for our reaction rate constant. And if our change in concentration over time looks something like that, then our change in our reaction rate changes with time. Taking the derivative, it ends up a linear line. Okay, so these the reaction orders, explicitly because we defined it by this exponent, are essentially just derivatives of one another. Finally, even though we're not going to use them very often, the rate of change for a second order reaction Again, for a decay, would look pretty sharp like this. That means the rate of change of our rate of change is going to be like that, something like that. Okay, and in this case, the units would be liters per milligram per second. Okay, so that's what we need to know about the reactions. That gives us how to write the piece that goes into the growth or decay reaction within our mass balance. Really, all it is knowing whether or not it's first order, second order, zero order, knowing that that means we need some power, some concentration to some power, might even be zero, so the concentration drops off completely, and knowing that that's what we're going to put in there for the reaction that happens in some volume. Okay, so then let's talk about the reactors that we might put this in. Again, we're going to deal with ideal reactors. That simplifies things. The tracer test I showed you, we can use things like that. We can do analyses for non-ideal reactors. For the purposes of our class, we're going to keep it a little simpler and deal with the principles for ideal reactors. So we have three primary types. I've already in some way mentioned them to you. One would be a batch reactor, a lot like a bottle, some sealed container. It's well mixed in the ideal state, and you have some reaction. So if you have a reaction going on in there, there's no inputs or outputs, so the accumulation is equal to the net reaction. Okay, it becomes very simple. The next would be what we call a continuously stirred tank reactor, CSTR. Some people call it a CMFR, continuously mixed flow reactor. Whatever you want to call it. Our book calls it a CSTR, so that's what I'm going to go with. It has an input, at least one, and an output, at least one, and it is well mixed in what would otherwise be a batch container, right? So this would actually be like your swimming pool if you have a hose going in with water going in and with some drain or overflow going out. A pond would be an example too if it has some stream feeding into it. Now a puddle with no stream coming in or out would be a batch reactor. Okay, so that's a CSTR, and the pond would have to be mixed enough too, by the way. In an ideal case, it's perfectly mixed. Whatever's coming in, that flow rate will be the same net flow rate that's going out. And there we go. The last one would be a plug flow reactor. And I think I have all these written out as expanding the acronyms here, but I'll just go ahead for you. Plug flow reactor is a lot like a hose. The water at the at the tap where you turn the nozzle has different characteristics than what's all the way at the end of the hose, potentially. They're not mixing. So if you've left a hose out in the Louisiana sunshine and it's filled with water, you turn it on and you want to drink from it because you're a little kid playing outside, you don't want to drink the water right away. You want to let it pass through because the water doesn't become cold right away or colder. It's all hot until it pushes out everything from there. It's like a plug of cool water is coming in and it finally makes its way around and gets to the end. That's the plug flow dynamic. What's at the end of it is not mixing with what's at the beginning. Rivers and streams also are modeled best by plug flow reactors because you're not mixing a mile downstream with what you have here, right? So the dynamics there are different than maybe a pond that's being mixed around by the wind all the time. So plug flow reactor, that's different than the continuously stirred tank reactor. And as you might see, each piece here can change the way we're going to set up a mass balance for them. In the case of the CSTR, that's a little bit kind of the most straightforward in terms of where we started. We have an input, maybe some reaction, and an output. If we assume it's mixed, then that's a CSTR. That means accumulation rate is inputs minus outputs plus reaction. The batch case is a little different. there's no inputs or outputs. So if there's accumulation, it's just whatever the reaction is doing. The plug flow case is a bit of a hybrid. In fact, the easiest way, and the way I'll go ahead and teach you, there's a couple ways to derive the same math, but the easiest way is to consider that the plug of water that's flowing through, it's not mixing with its neighbors, so it acts like a batch reactor all by itself that just moves along for some time and eventually gets dumped out. So what we'll find for the derivation of the batch reactor is if it's going to react, we're going to give it some amount of time. Time is the only thing we can change. We can't change the flow rate. So we give it some time. For the plug flow reactor, the time is actually the hydraulic residence time that we learned about. So then we can change the flow rate to change the amount of time the water has in the reactor. Otherwise, the math turns out to be pretty much the same. Yeah. Exactly. Yeah. The other way to do the math is to treat it as an infinite number of very small CSTRs, where you have something coming in, mixed within it, and going out into the next plug, and so on. Either way you do the math, we can get there. I'll mention this again later, but either way you do it, that's the way I think is simplest, is to treat it as a tiny little batch reactor, has a reaction going on, and eventually dumps out the other end. So whatever happens in that one batch reactor should be the same with any batch reactor that's flowing through. So any parcel of water, any bit of water that's flowing through the system, that's going to happen to it. Okay, so a little more in depth for each one. Batch reactor, the accumulation rate is going to be equal to the net reaction because we have no inputs or outputs by definition. That means when we set up a mass balance, if there's no reaction, there's nothing to do, nothing to solve. So generally for a batch reactor, we're going to have a reaction. But that does make it kind of simple because our accumulation rate, we said, was V dc dt. And this is going to be equal to plus or minus the reaction in that volume, right? R of C times the volume. Now, this is an easy moment where we could look at more than one reaction and say, okay, accumulation, you have some negative reaction plus some positive reaction. How's the balance? Or we could just say, over time, bacteria are dying from the tiny bit of chlorine, or the chlorine that's remaining here is dissipating slowly. So we could say something like, well, it's the same volume. We'll go ahead and cancel those. We can then say dc dt is equal to, and we'll take an example, right? We'll take a zero order growth. Okay, that would be a positive k times c to the 0 power. dc dt equals k. My example from earlier, $20 per time, right? Per day, per week, whatever. That's just what it is. That's your accumulation, right? You could do your budgeting this way. Okay, you have this many inputs, this many outputs. What's happening? If you wanted to budget and have your interest rates accounted for, then you need some first order math in addition. But this would be the simple form, right? There's no flow rates coming in or out. There's just that reaction rate. Okay, for a CSTR, we've spoken about this already. It's not always at steady state. Sometimes it's at steady state, or it could be, right? So we have V dc dt equals what's coming in with an input rate. That'll be a Q C initial minus Q C final plus whatever reaction R of C times that volume. One thing I'll say here, it's important to notice, we have an initial concentration going out and a C that we might call final here, and a concentration inside the reactor itself. Well, it turns out that C, if this is well mixed, is going to be the same thing as what's going out. This provides some interesting circumstances for design because as soon as we add in water to this, let's say we're removing something. We're killing some bacteria in this reactor, let's say. As soon as we add some water, it is diluted. So our concentration drops immediately. That's important for a few reasons because one, if the reaction depends on how much stuff is there, there's not as much stuff in there to react with. So the reaction's actually a little slower than it could be. Now, it's also helpful because it's an immediate drop. And whatever is going out is now treated because this continuous reaction is depleting whatever that stuff is. So there's a few reasons this can be beneficial or not as ideal as a plug flow reactor, but it's just a characteristic. Whatever is in here, because it's well mixed, is immediately the same thing that's going out. Okay, so C that's inside here is the same C that's being discharged. That means when we do this math here, I just write C here. I don't need the C final. I can just leave it as C because that's the deal. That also means the C that comes out, let's take a first order decay as an example. This will look like V dc dt equals QC naught minus QC minus VK times C to the 1 power. So VKC. Right? Of course, we can go on and derive that and solve for something, but this is our mass balance equation before solving for anything. This is just kind of our starting point. And we see that that C is showing up in a few places. Okay, does that make sense? And you could see if I asked you to do the same thing and set it up with a zero order growth equation, you could do that. Right? To do that, it would have to be a plus for the reaction term and a C to the 0 power, right? So based on the reaction order, we're changing what we're adding in to that reaction term. So the reactor type and the reaction type are independent. Doesn't matter what jar, what thing you put this in, the reaction itself is different than the reactor. And that's kind of what I want to stress today and show you how the math works out with that. So the plug flow reactor, these are continuous input and output. And our assumption about mixing, if we think back about that tracer test I showed you, if it was ideal, then that blue line would just be an exact perfect line flowing through, nothing, no leading edge, nothing dragging behind. It would just be a perfect flat tracer and it would all leave exactly at the same time. That would be an ideal plug flow reactor. So we're assuming perfect mixing within that plug, that little slice of water that's moving along. And no horizontal mixing at all. And that's the reason that if we just take one slice and follow it along, if it's not mixing with its neighbors, but it is mixed kind of vertically or within itself, then it's essentially a batch reactor that's just moving along. That means what we can describe, if we just take one plug, we can do the math on the accumulation for one plug of the water. We would have V dc dt equals no inputs or outputs because we're assuming there's no crossing. 0 minus 0 plus whatever reaction, plus or minus, that's happening in that volume. Okay? And the volume here, if we assume that what's happening in one plug ultimately happens throughout the whole thing, we can use the reactor volume as our volume here. It's going to cancel anyway with what's on the left. And then the question becomes, when we do the derivation, we'll show in a few minutes, that time, instead of time, we use the residence time, the hydraulic residence time. So we know the time feature that we would have used for our batch reactor math should be simply the hydraulic residence time, because it's a batch reactor that sits in there for some amount of time undergoing the reaction. Does that make sense? So sometimes we do things like ultraviolet light dosing, might be a flow-through system. It's getting a constant amount of irradiation, and we'll have a first-order reaction. The bacteria are dying away, the viruses are being killed based on how much light they're receiving, and they're staying in there for some amount of time. So if we increase the light dose, we can do it in a less amount of time, have a higher flow rate. That's the type of balance that we can do and understand what's happening with this kind of mass. All right, so let's do a couple derivations. And I'm going to give you a moment to work this out on yourself, on your own, or with each other. Feel free. So for a batch reactor, let's derive the math and solve for, let's go ahead and solve for C. What you'll notice, if I just tell you to solve it, you're like, wait, what do I solve for? C might be a default, but you could be solving for time, right? With time equals x, y, z, right? You could rearrange the mass balance to solve for a different parameter. So that's another piece that you're going to need to recognize is you could rearrange our mass balance equations for what you need to solve for. And that's a key skill for the course. So take a moment. I have the little starting point there for you. Derive the zero-order decay reaction solving for C given some volume. So hopefully you began solving and realized I'm making you do a little bit of calculus. Thankfully, it's quite simple right now. Occasionally, we need to do some mass balances that require some calculus, right? So we start with V dc dt. For a batch case, we have no inputs, no outputs, right? This is just a batch container, well mixed with some reaction going on. So it's 0 minus 0. It's a first order decay reaction, so this will be a negative. In that volume, we have the reaction occurring. So V times K times C to the 0 power. Okay, that means we can rearrange and say the V's will cancel, the C goes to 1. So it's dc dt equals negative K. And then we just simply need to integrate. So I'm going to do that by integrating from C naught to C. So a starting condition to a final condition is a nice way to describe that. dc equals negative K times the integration of dt from 0 to some time t. That's just going to give us t, essentially. So this will be C minus C naught equals negative kt. So C equals C naught minus kt. If you're thinking this looks a little obvious, you're thinking correctly, right? In the simplest cases, it's kind of obvious what happens. We didn't really need to have calculus to know that if I take $20 a day from you, your amount of dollars after 10 days, if you started with, 200, will be 0 by the 10th day, right? You could do that math without the calculus or without the mass balance. But what I'm showing you is we get there, and we get there correctly following this procedure. So let's go now and do the first order decay. You'll need a little bit of calculus and to remember one little trick for this one. But once I remind you, if you don't catch it yourself, you'll be like, oh yeah, I learned that. No problem. So give this a minute. I'll work it with you as well and give you that reminder. So really two, one's algebra, one's calculus. It'll make sense. And you'll realize you've seen this a lot before. All right, who knows the calculus here? You remember? Yeah. So what is the integration of dx over x, ln of x, right? You've seen it before in calculus. So it's just a matter of remembering that that's the deal here. So we end up with the natural log of c minus the natural log of c naught equals negative kt. Now the other trick, so to speak, is to recognize that natural logs you can combine. One minus the other would be the same thing as taking the natural log of c over c naught. Equals negative kt. So from here, I'll just go ahead and move this up here. We can solve for c by taking e to the power of both sides, and we will get c over c naught equals e to the negative kt. Suddenly, this is looking quite familiar, I bet, right? The interest rate equation, things like that. We can then solve further if we're going to c and solve it as c equals c naught times e to the minus kt. Okay, makes sense? All right, so just a couple of mathematical things you got to remember there, and then you can derive this no problem on your own. You could do this for a growth equation too, and I recommend, if you think that it might be at all difficult, just go ahead. Derive it that way also. So the point here is that you're completely able to derive from this principle of a mass balance to an equation we can use. So if I asked you a problem, let's say we do a bunch of these and solve for concentration. And then on an exam, I suddenly ask you to, I give you the concentration, I ask you to solve for the starting concentration. Well, you have all of the tools to rearrange this, solve this, and rearrange for C naught instead of C, right? This is the power of this approach is that you can use it for what you need it for, given that it's set up properly. So that's, you'll see, sometimes we'll solve for C naught. Sometimes we'll do an efficiency. How does C compare to what we started with? Maybe C naught minus C. How much removal did we get per C naught that we started with? Maybe we'll solve for the time, maybe the rate constant. We can do a lot in a lot of different systems with this type of an approach. So I'll say also that this same process works for the plug flow reactors if we, instead of take the time, we put in the hydraulic residence time, the theta. That also means we are suddenly accounting for the operational parameters, the flow rate and the volume, if we consider a plug flow reactor. It's still going to be a time unit, and it still plugs in to where the time is on those. Okay, but the underlying math to describe it is still right there. We could do this for the second order. The calculus does get a slight bit more complicated, but it's another lookup, right? What is the integration of dx over x squared? Right? You've probably seen that before. That's what we would need for the second order. Before we go there, if we go there, let's do this. And I think I'll wrap up on this slide, but let's do this for the CSTR case, where we have an input and an output. Let's go ahead and solve for C again, just keeping it pretty simple. So solving for the C final, and this is a CSTR, meaning we do have an input and an output, and either a zero order decay or a first order decay reaction going on inside. One other assumption, let's go ahead and assume we reach steady state. Might be interesting to solve without steady state as well. No, steady state means the accumulation that goes to zero. Because we can still have a difference in what's coming in versus going out if there's some reaction happening. Steady state is meaning that the accumulation goes to 0. So that means the amount of stuff in our chamber is at a steady condition. Yeah. It's maybe a bank account will be better than the hose example, the pool example, because there's a concentration in, yeah. So the pool example is not my best. The bank account might be a better one because you might have inputs and outputs and maybe some reactions happening, but you've reached a, if you're operating it in some way, you might have an even ledger over time. If there's no reaction, then the Q's are equal. Well, the Q times C is equal. Right? The best way to describe that is to say that this term on the left, the accumulation, which we've been writing as V dc dt, goes to 0. It's helpful, I find, to be able to visualize or conceptualize what that means, though. And that's not very straightforward. Okay, so for the 0 order decay, I kind of had you start here, the steady state meaning V dc dt, that's our accumulation term within that control volume, is 0. So then that is set equal to the QC naught. That would be what's coming in if we decided to put a Q. This is a very generic way to describe it, by the way. If you put 2 different Qs and 2 different inputs, okay, you could balance it that way. But we're just keeping it simple. 1 Q in, 1 Q out, and some concentration coming in, some concentration leaving, okay? So in that condition, then we have QC naught minus QC minus VKC to the 0 power, meaning that C goes away. Then it's a bit of algebra to get it to QC equals QC naught minus VK. Divide everything by Q. We get C equals C naught minus V over Q times K. And V over Q, we've seen, that's our theta. So that's kind of nice. You don't have to put it in there, but it simplifies it even a little further, something we often use. And this is part of why. So we can get a mass balance to solve for C like that. Now, I'll give you 1 minute to do this, and I'll start working with you on it, to do the first order decay reaction. We're going to see this one a lot. Yeah. Yes. All right, so real quickly, we have the accumulation set to 0 for steady state. Going to be the same otherwise, and then we have the reaction term including c to the 1 power, so that c remains as just c. So then if we get the c terms by themselves, add them to both sides, get them on the left, it's qc plus vkc equals qc naught. I like to divide by q at some point, maybe this stage. That'll give us something a little simpler, c plus, I went ahead and put v over q as theta, so c plus theta kc equals c naught. Extract out that c, so I have c times 1 plus theta k is equal to c naught. So c becomes c naught over 1 plus theta k. Sometimes we'll see c over c naught equals 1 over 1 plus theta k if we solve for the ratio. Okay, so I'll leave it there. We will pick back up essentially on this slide in case there was some questions or you wanted to go over it again, any of that. And have a good weekend. We'll see you on Tuesday.